Hey class, let's work on a couple problems that will help you with your homework. So problem 9.22 on page 308 of our textbook. The manufacturer of cans of salmon that are supposed to have a net weight of 6 ounces tells you that the net weight is actually a normal random variable with a mean of 6.05 ounces and a standard deviation of 0.18. Suppose that you draw a random sample of 36 cans. Part A. Find the probability that the mean weight of the sample is less than 5.97 ounces. Okay, so what kind of problem are we working with here? Well, what's our sample? What is it we're sampling? We're sampling cans of salmon. And what are we doing with these cans of salmon? We're weighing them. Right? So this is a continuous variable. We're weighing them. It's not a binomial experiment. Right? We're not saying, is this can blue or not blue? We're weighing it. It's going to give us a continuous distribution, and we're going to take an average of all of our weights. So if we know that, then we're dealing with x bars and mu's. We're not dealing with p's and p hats, right? Because we're taking a continuous distribution, and we're not taking a proportion, or we're not doing a binomial experiment on something. So first of all, let's do a little bit of maybe some drawing. Let's see, so here's our normal distribution of our sample means, and what is our mean? What should actually have happened? 6.05. So it says something has a net weight of 6 ounces. This is to throw you off. But they actually tell you that it actually has a 6.05 ounces. What that means is that the can says 6 ounces. Right, but really in the factory they're shooting for 6.05 ounces. Right, that's so that they're safe. They're not getting so 6.05 is what's expected to have happened. The six thing is they would just kind of throw us off. So 6.05, but we go take a sample, and we want to find what's the sample of less than 5.97. So that's over here somewhere. We don't know exactly where it is, but 5.97. All right. And we want to find the probability of something that's less than that, so less than that's over on this side, right? Okay. Alright, so this is the problem, right? So we actually have 2/3 of everything we need, right? We have what was expected, 6.05, what we got. So the only thing we need now is sort of this spread, what the standard deviation of this thing is. And it's actually a standard error because we're dealing with means. Right, we're not dealing with single cans. We're dealing with a mean of a certain amount of cans. So let's talk about this. So here's our mean. What was our mean? 6.05. This is what was expected, right? What was expected. And we have a standard deviation. It was given to us. Standard deviation was 0.18 ounces. And then we went and sampled that we have some kind of N. And how many cans did we sample? We sampled 36 cans. 36 cans. And from that we can come up with a standard error, right? And the standard error, if we're dealing with means, is what? Just sigma divided by the square root of n, right? Which is sigma, standard deviation, divided by the square root of n, like that, right? So 0.03. Okay, so now we can find out what this problem is, just using the norm dist function, right? So this is the left-hand side, so we just use the norm dist, where x is what we got. Oh, I don't have that written down anywhere. So we put that right here. This is what we call x bar, right? This is what we got, 5.97. What we got. All right, so now let's do it. So we're really trying to find the probability of an x bar less than 5.97, right? Given this distribution that we drew over here. Okay. Let's do it. So equals norm dist. Oh gosh, equals norm dist. X bar is what we got, comma, mean 6.05 is what we expected, with standard error, because we're dealing with means, not individual, standard error, and 1 is cumulative. Alright, so 0.0038, so pretty small, if that was the case. So let's see. That was part A. Part B. Suppose that you ran a sample of 36 cans of salmon to produce a mean weight of less than 5.97 ounces. Comment on a statement made by the manufacturer. So what would we say if we got this result? Is basically what it's asking. Well, we would sort of question the manufacturer and say, well, according to our sample, that the chance that that your actual real average is 6.05 is very small, right? Smaller than 1%, 0.00. So what is this? This is 0.38%, right? So not even a 0.5% chance that that your mean is right. All right, so that's 9.22. Let's look at 9.23. 9.23 says a number of customers who enter a supermarket each hour is normally distributed with a mean of 600 and a standard deviation of 200. The supermarket is open 16 hours per day. What is the probability that the total number of customers who enter the supermarket one day is greater than 10,000? And then it gives us a hint. Calculate the average hourly number of customers necessary to exceed 10,000 in one 16-hour day. All right, so again, what kind of problem is this? Was this a binomial experiment? No. Well, first of all, what is it we're sampling? Well, we're sampling, this is actually kind of typical. What is it we're sampling? Are we sampling the number of people, or are we sampling the number of days? So, the number of hours per day, the supermarket 16, no. This would probably be the number of customers who enter the supermarket in one day. We're actually sampling the number of hours. What are we doing? Every hour we're counting how many people come in, right? So we're measuring how many people come into our door, and every time someone comes in, we just count. That just counts as 1, 2, 3, and we do that for every hour. So every hour, the hours is our n, right? So here's n. How many hours in each day? Well, there's 16 hours in a day according to this problem. And before we go a lot further, let's draw what this looks like. Okay. So here's our distribution. Wow, it's quite a distribution today. Here's our distribution, and our mean is, well, what does that mean? What is this expected? So this part's a little bit tougher for us. So actually, it's not too bad. The mean of 600, it says that. So mean of 600. 600. Okay. The part that's hard is what it's asking us. So it's saying, what is the probability that the total number of customers who enter the supermarket in one day is greater than 10,000? So this is per hour, right? So this distribution is 600 per hour. They want to ask, the question is, what's the probability of more than 10,000 per entire day? So how do we do that? Well, the easy way to do that is to convert that hourly thing that daily thing into hours. So this is per day. 10,000, right, which per hour, how do we turn that into per hour? Well, just that guy divided by 16 hours, 625. So what does that mean on our picture over here? Well, there's some number over here, 625, 625, and we want to find the probability that something's bigger than that, I believe, right? Yeah. So it is probably something's bigger than that. Let me show you why in a second. I'll color this so I remember. 625. So why is it bigger than 625? Well, what if our probability was 626? All right. What if our average hourly rate of people who walked in was 626? How many would we have totally at the end of the day? Well, that's 626 times 16. Let's type in 16. Well, I have 10,016. So 10,016 is more than 10,000. In fact, if I do 625.1, now I have one person more than 10,000. So that's answering our question, the probability greater than 10,000. So there is some homework problems like this where you have to convert something that's in a bigger unit into a smaller per hour unit. Okay. So what is our mean? Our mean is 600, right? So on average we have 600, and we have a standard deviation that's given to us. Standard deviation is 200. So all we need now is a standard error, which equals what? Standard deviation divided by the square root of n. So n equals 16 because we're doing 16 hours, right? So every hour counts as a new sample according to this problem, right? The way this problem is set up. Oops, this guy got a little bit weird. So this was 10,000. 625. All right, so what we want to do is find the probability that some x bar is less than 620. Oh, sorry, not less than, greater than 625. All right, so this is our x bar. So what this problem is saying is that what happens if you were to sample, 16 hours, and you just averaged every hour, right? So you had 16 data points. You averaged every hour. What happens if your average was greater than 625? That would mean that your total sum would be greater than 10,000. And maybe in a second I'll show you why that is a little bit more visually. But this is pretty easy. Once we know how to do this, we can solve this problem, right? So this is just equals 1 minus norm dist. What we got is x bar. What we expected was 600 as mean, and standard deviation is actually a standard error because we're dealing with means, not individuals, not individual things, and 1. So 30% chance. All right, so let me see if I can set up a little experiment, and maybe this will make this problem a little bit more clear. So let's see, if I have 16 hours, so hour 1, hour 2, 16 hours. Let me see if I can move this guy over a little bit. Zoom back. Let's see. There we go. 16 hours, and for each one of these hours, I can actually come up with sort of simulate the number of people that come in. And how to do this? I use this norm inverse function. Well, first of all, remember the rand function? Gives us a probability between 0 and 1, right? And then if I use this norm inverse function, and then use that as our probability, right? The rand as our probability, with a mean equal to 600 up here, F4, and a standard deviation equal to the standard deviation, they give us F4. Then this will give me the random number of people that would come in that day, at that hour. So in this hour, 623 came in, if hit F9, 608, hit F9, 694. Right, so I can do this a whole lot. All right, so let's just change this guy right here into a rand. So you would never have to do this, but this is just to help us understand what this problem is asking. All right, so copy this, paste this all the way across. Now what the question is asking is, what's the average of all those 16 hours? Well, in that case, it's 625.58, right? So if that's the case, this is the average. I can also find the sum, right? The total number of hours for the whole day. So here we go. So this should maybe be helpful. So here's 624. Our sum is just under 10,000. If I hit F9, I get a new, so that's quite a bit smaller. Here we go. 634 is our average. We're just over 10,146. So now we can sort of play around with this just like we've been doing. Experiment 1. Let's see if I can make this go a little faster. Go down to maybe 10,000. And paste this guy down. Alright, so here's 10,000 experiments. Now we can sort of ask the same question. What's the probability that I get something that's greater than 625? So let's write that. Greater than 625. We did this in class, but I can do a count if, right? Here's my range. Hit F4, comma. I don't really hit that guy. So I got 3,028. Divide that by 10,000, and I get really pretty close. So I got 3112 here. The answer I got with a theoretical model is 0.3085. So if I hit F9, that number will change just a little bit every time I hit F9. So there, that one's really close. I like that one. So there you have it. So that's all that we're really, finding. In fact, the real question was, greater with the sum. The sum is greater than 10,000. 10,000 hours. Well, this is the same thing. We can do equals count if, but instead of doing the average, we can do the sum. And count that. Look, it's exactly the same number. Right, so an average, this is average. Average greater than 625 is the same as summing is greater than 10,000. So you can see it's exactly the same. All right, so there's that. Hopefully that will help with some of your homework problems. All right, see you later.